In this video, I'm going to be going over a method for fine-tuning machine learning models called IA cubed, and I implemented it recently for Stable Diffusion using the diffusers library. Here's an example of Stable Diffusion generating an image of Donald Trump, and I fine-tuned the model using this method on a data set of Pokemon artwork, and it produced this output. And with that artwork style, here you can see some of the data from the data set I used here on Hugging Face. You can see this is the artwork style that it was going for. I think it did a pretty good job. And something really cool about this is that these changes to the model are much smaller than a LoRA, for example, a low-rank adaptation file. Those tend to be up to 100 megabytes. And this one tends to be less than 1 megabyte. Here it says 222 kilobytes, but it's actually double that for this example. I had additional learned vectors that I'll go over later. You can see I implemented it for the diffusers library. So let me go and explain a bit about how this works. So here's the paper for IA cubed. The main part that you'll need to know is this formula right here. But some people might not be able to understand this just by reading this formula here. So I made a bit of a drawing to explain it. So every cross-attention layer in Stable Diffusion operates on vectors called keys and queries. So I'll start here. You could think of each set of vectors, like here I have 4 keys, which is 4 vectors, which you could think of as a matrix that multiplies by a matrix of 4 query vectors. But the easier way to interpret it is as each item here being a dot product of 2 vectors. So the keys that are more similar to the queries will have larger values in this matrix here. And so this is a matrix. Each of these will be a scalar, and there is a square of them here, and they will be larger when the keys are more similar to the queries. That's the main takeaway. So far, everything here is just normal in Stable Diffusion. And the keys are generated based off the embedding of your prompt, and the queries are based off of the content of the image. And here, the next step is to convert each of these into something similar to a probability distribution with the softmax function. So some of these will be bigger than others. None of these are designed to really match any size. I just kind of drew this by hand. But here you end up with a distribution, and you multiply each value by its amount in the distribution and add them all up, which is similar to taking a weighted average of these value vectors to finally get your output value vectors. And here, now I can explain the changes that I added with this IA cubed method that I found. So the basic idea is that for each key vector, you will scale each of these up by a different amount. And that amount is what is learned in the fine-tuning. So initially, they will all be multiplied by 1, and you will gradually adjust them to multiply by values other than 1. So initially, it'll just produce the same output as a non-fine-tuned model. And a nice property of this is that all the multiplication here is associative. which means that you could, it's called merge the weights, which basically means you change this weight matrix by multiplying all of its columns by the values from the learned weights. And after you do this step, you don't need to multiply by the learned weight here anymore, which means that the architecture will fundamentally be the same after fine-tuning, which is a nice property that lets the model be more compatible in other places after being fine-tuned. It'll also make it such that you don't need to store the changes or the learned weights. Also, something similar with the keys happens with the values. You will scale up each of the value vectors by a certain amount. And this will start out as at 1 for each of the vectors. And you could do the same trick where you merge it with the weight matrix. So you end up with a model with the same architecture. And all this lets us do is fine-tune parameters in the model indirectly. And the part that we learn is a lot smaller, taking up a lot less VRAM and letting it learn faster as well, because there's less parameters for gradient descent to operate on. And here you can see it written in code. A lot of this is boilerplate code from just a basic cross-attention processor. I based it off of there's a built-in one for LoRA, and I changed everything up. This is the main part that I was talking about earlier. You can see one difference with my implementation here is that I initialized the weights to 0, and I also added biases. Those are not compatible with this. That'd be like adding a bias like this right here. You can see that doesn't have any way of being merged with the original weight matrix. So that might be preferred, it might not be. But for all the examples I used, I did have learned bias vectors. And one thing I did here is I initialized the weights to 0, but I set them up as a almost residual connection by adding them here. So it would be equivalent to having them start at 1. You can see like it's almost like a distributive property here. Basically, it lets the weight decay make more sense. Like weight decay is based around weights being on average around 0. So I wanted them to start them at 0 when nothing was being done. So this is the only real change here. Is you add these learned vectors that change the key and value vectors. And the rest of it is just going through the layer as normal. So that's mostly it. I think it did pretty well. This took about maybe 45 minutes of training on a 4090 I rented. So it didn't take that long, especially considering that it wasn't using any special fine-tuning methods, like Dream Booth, for example. Yeah. I feel pretty good about this. Maybe it has potential. I don't know if it's better than LoRA or not. My guess is that it's not, but it's kind of cool how it has much smaller parameter counts and file sizes. So it could be useful for something. That's all for this video.